Welcome to all. I am Ms. Anuprita Bhosle, presenting the seminar on Introduction to STL file format. So, what is a STL file? STL file is the standard tessellated language. First, we have to create the model in CAD software. There are various CAD softwares available in this for this preparation of this geometry, and we have to convert this CAD model file into the STL file. There are various techniques available to produce the 3D prototypes. 3D printing is one of them. Most of the 3D printing devices uses the STL file. The STL file contains the tessellated triangles. The surface of the geometry can be divided into number of the tessellated triangles which are approximated. Consider the block here, and this block is divided into number of the triangles. So each face is divided into 2 triangles. So there are 12 faces for this entire cube. Triangulated surfaces. Any 3D form can be approximated by the triangular surface. So the geometry which is 3D, this can be divided into number of the triangulated faces. So the polygon or the more sides can be divided into the triangles. On computer, these are represented by the list of the vertices which can be counted in the anti-clockwise direction. The vertex can be described by the XYZ coordinates. The figure shows the number of the tessellated triangles which is consist of the STL file. In this way, the surface of the geometry is tessellated into the different number of the triangles. Polygons divided into the triangle. The figure shows the polygons with the 4 sides, 5 sides and the 8 sides. Here the polygons are divided into the different number of the triangles. The formula is to calculate the triangles is, and n-gon is represented as n-2 triangles. Here the number of the sides in the first figure is 4. So 4 minus 2 is equal to 2. So the number of the triangles is equal to 2. For 5 sides it's 3 and 8 sides is 2. Then triangles in a space. Consider the triangle having the vertices 0, 0, 0, 0, 1, 0 and 0, 0, 1, having the red arrow pointing outward, which is nothing but the normal, having the coordinates 1, 0, 0. Every vertex has XYZ coordinates. Then list the vertices starting with the any of 3. Then list these vertices in a anti-clockwise direction, which when we see from outside it should look like a counterclockwise. Then normal vector point out from the object. Use right-handed XYZ axis. Next is a right-handed coordinate system. The left figure shows a left-handed Cartesian coordinate system, and right-handed Cartesian coordinate system is at right side. Then consider this tetrahedron. The tetrahedron consisting of the number of the triangles which are shown by the capital letters A, B, C and D. The A triangle can be shown by the vertices 1, 1, 1, minus 1, minus 1, 1 and 1, minus 1, minus 1. Similarly for B triangle, the vertices are minus 1, minus 1, 1, then minus 1, 1, minus 1 and 1, minus 1, minus 1. Similarly for C and D, the vertices should be taken. All these vertices should follow the anti-clockwise direction. So, there are many 3D file formats exist for the 3D printing. STL is one of them. So how to make the part which I want? Actually, what happens after creating the part in the 3D prototyping, we don't get the exact shape whatever we assume, because there is a data loss during the conversion of the CAD data file to the STL format. So there are some key shape optimization settings. First is angle deviation and chord height. Next is wall thickness. Third is inverse normal edges surfaces, and next is multiple shells or the nested parts. First is angle deviation and chord height. The smoothness and the roughness values depend on these 3 factors. These are the main 3 factors which can use to define the surface which is smooth or rough. If we want too much smooth surface or rough surface, then we have to vary this angle deviation and the chord length parameters. So there are three figures which indicates the coarse faceting, excessively fine faceting, good quality faceting. So first is coarse faceting. The main disadvantage is that after creating the part in the 3D modeling, coarse faceting produces the face spots on this surface of this geometry, surface. So this is a poor, having the file size 705 KB. The coarse faceting causes because of the large angles or deviation, and the chord length becomes high, or the combination of the both. Excessively fine faceting is having the file size 17 MB. Actually in this the angle is very less, deviation and the chord height is also less, therefore it produces very fine faceting. Actually we don't need such type of the fine faceting, because it will take more time and cost to create the 3D part. Then next is good quality faceting. By adjusting these three factors, angle, deviation, the chord length, we can achieve the good quality faceting, having the file size much more less than that of the fine faceting, which is 2.7 MB. Then next parameter is the wall thickness. The wall thickness should be wider as much as possible, because if we use thin wall thickness, the problem arises in the tool path calculation. So consider this example. In this the red line shows the cross section of the surface, and the green line shows the tool path generated. So here in this arrow which is pointing towards this area, the thickness is very small, so we can't calculate the tool path generated or the tool path calculations. But in the above feature we can calculate the tool path, because the area is much more wider than this area. Next is inversed normal edges surfaces. The yellow line in this sketch represents the curves in this sketch, and the red line represents the error. The model which is to be created should be watertight, and therefore there are various CAD softwares available which allows the surfaces to be very close to each other or intersecting each other, so that it will become watertight. There are various these STL viewing tools are available to find out the errors in the STL file. Multiple shells of the nested part. Every part in the assembly should be saved separate STL file. It should not be assembled, otherwise it will create the files with nested parts. We don't need it nested parts, so we should keep different part files having the STL file. Then the STL file format should fulfill the following specifications. First is the normal, and each vertex of every facet are specified by 3 coordinates each. Next is each facet is part of boundary between the interior and the exterior of the object. Third is a vertex to vertex rule, which defines the triangle should share 2 vertices of the each adjacent triangle. Next is all vertex coordinates must be positive. Then STL file format. The STL file format consists of the 2 data formats. First is ASCII and next is a binary format. ASCII format is more descriptive and human readable, and the file size is lesser than the binary file, because binary file is larger as compared to the CAD file. It consists of 80 bytes header file, which includes 4 bytes the total number of facets, then 12 bytes each coordinate represented as 4-byte floating number, 2 byte spacer between each facet, which results in each facet is represented by 50 bytes, 12 for normal, 36 for vertices and 12 for the spacer. So this is the common STL file format for the 3 triangles it is shown here. First we have to provide solid and the name of that part. Then for triangle 1, 7 lines will be there. Similarly for triangle 2 and triangle 3, then end solid and again name. This is the algorithm which is showed for the one triangle only. First we have to specify the facet normal in xyz coordinates, then outer loop, then vertex, 3 vertices of the triangles in the anti-clockwise direction, then end loop, then end facet. Only xyz parts need to change for the each triangle, so it is easy to copy and paste in the editor. These are the some examples of the STL file format in the ASCII format. So here only we have to change the vertices of the triangles and the facet normal, otherwise all the algorithm will be same for each triangle. Thank you.